Hello, everyone. In this video, I'm going to talk about heaps and priority queues. A heap is a full binary tree data structure, except possibly at the leaf level, where each node holds a number. A heap can be formed as a max heap or a min heap. In a max heap, the number on each non-leaf node, which is a root node of its subtree, is greater than or equal to the largest number among its children. In other words, the number on every node in any given subtree is less than or equal to that on the root of the subtree. So if we look at a drawing, so we can think of a heap. First of all, is a balanced binary tree, which is a heap. Okay, so you think of here, I have a root, and then I have a left subtree, and I have a right subtree. And if this is a max heap, then it means the number here, let's say the number on the root is x, then x is greater than or equal to any node of among its children. Okay, so x is greater than or equal to any node on its left child and on its left children, and also is greater than or equal to on its right child. So this is you can think of it here is the x is greater than or equal to any node. I can think of maybe we can think of L value, and x is also greater than or equal to its right subtree and then its value. So in other words, if we implement a priority queue, then we know that x is always the largest one among its children. So we just need to look at its roots. And also L and R are max heaps. Okay, so which means that for any subtree, uh, for any subtree, it's also a max heap. All right, so hence a heap is a priority queue. So we can think of that way. And as a matter of fact, heaps are designed to implement priority queues, and later on we'll see that heaps can also be used to sort numbers. But you can think of heap here is a heap is the same as a priority queue. So that would be the appropriate way to think of heap. And priority queue, we could have a max queue or a min queue. So max queue means that if I want to find the largest number from a queue, I can do it in constant time, which basically is just the root. Likewise, if I have a min priority queue, then if I want to find the minimum number from the queue, then I can also do it in constant time. So after I remove this root from the heap, then I will have to maintain the new tree to be make sure the new tree is a heap. In that case, we will need to involve a routine called heapification. All right, so that's the concept of a heap. So next we're going to see how we can construct a max heap, and constructing a mean heap would be similar. So here we are going to first view a linear structure as a binary structure. So let me open up a whiteboard here. Okay. So let's assume that we have a list, and so this is the index. So what I'm going to have is that I'm going to place, now this is a linear, right? So this is a linear, but I can view A as a balanced binary structure. So I would like to emphasize the word viewing, right? So we don't change, we don't actually change the list, but we just view it as a binary structure in the following way. So A0 is the root, and then A1 will be its left child, and A2 is the right child of A0, and then A3 and A4 are the A3 is the left child of A1, and A4 is the right child of A1. And then this would be A5 and A6. So we keep on doing this. So this is going to be 7, 8, and 9, 10, 11, 12, 13, 14, and so on. So if you read one level at a time from left to right, so we have the linear structure, right? So this is, so we start from 0, and then going this way. So that's 0, 1, 2, and then going this way. So one level at a time, but from left to right. So A3, 4, 5, and 6, and then we go this way, and then we go this way. All right. So at the last level, so only at the bottom level, it may not, for instance, we may not have exactly so the term here is a full binary tree. So this may not be full because at the last level, so we may not have enough leaves. Okay, for instance, now we that n is, let's say n is equal to 10. Right? So what we have here is A0, A1, A2, A3, A4, A5, A6, A7, A8, now 10. And these two nodes are leaves. So these are leaves. Okay. And then the last parent, so which means the node that's a parent with the largest index. So we can think that this is the last parent. So we can also see the following relations of a node with index I, then its children will be 2 times I plus 1 as a left child. And then now this is the index. 2i plus 2 will be its right child. So we can verify this one, that we start with I to be 0. So the left-hand side will be 1 and 2. And so for when I is equal to 1, then the left is 3, the right is 4. So we check this. And when I is equal to 2, the left is 5 and the right is 6. Right, so we have that. So that's general. Okay, so for any list, we can build a list in this way. So then now to build a heap, for instance, so to build a max heap. So what we start is from the last parent. So we start from here. Okay, so this is a tree. Okay, it has a parent. You may have one or may have two children. So what we do is compare the node on the root with its two children and place the largest one on the root. Okay, so for instance, we compare in this case, we compare A4 with A9 and also A4 with A10, and whichever is largest, it's going to be placed. So we just swap, right? So let's say A10 is the largest, then we will make this portion of it to be A10, A9, A4. So this is the largest. And then we are going to move to its sibling. Okay, we also do the same procedure. So once for this layer we have done, then we are going to move from the right. So move up to one layer or one level. And from the right, okay, so from the right, so then for instance, in this case, so one level up is this. So I have two subchildren or subtrees. They are already max heap. So what we need to do is compare the root with, so compare this root with its two children. So let's say A4 is the largest. So then we're going to place A4, okay, and put A1 down. But then we have to continue to heapify, so that, for instance, when we have this A4 down, A1 down, and then we compare its two children. The largest one will be moved up. So until we go down to the bottom. Okay, so that is heapification. So as you can see, heapification is always operated on one pass. Okay, so it could be here, just one pass. So this is a balanced binary tree. So heapification will only require a big O of H steps. H here is the height of the subtree. Okay, so H could start from the height could be 1 up to log n because of balanced binary tree. Okay, so heap is a balanced binary tree. It starts from a linear structure, but we view it as a binary structure, and then we do heapification. All right, so that means now to build a heap, okay, so we have n nodes, and so starting from the last parent, and so approximately we have n's divided by 2, many many internal nodes, and then think about each time. Each heapification is at most log n, so we have about n. So roughly, it will be n times log n to to make any list into a heap. So now let's go back to our slides. Okay, so I have just explained this part. So now let's look at its complexity analysis in greater detail. I also just mentioned the intuition, why it is n log n. So let's look at the detail. And for any tree, so for any subtree with a high age. So this is what I just mentioned earlier, but now let's just make it more formal. So for any tree with a high age, if this is a max heap, and if this is a max heap already, so to make the whole tree a max heap, we just need to start from the root, compare with its two children, and then the larger one will be moved up, and then we move down the smaller one, and we keep doing it. We keep heapifying. Okay, so it's only on one branch. So that means that to heapify a subtree with a high age would require only a big O of H steps. And this H is less than or equal to log m. Let's say the number of nodes in this is m. So, and then we start from the last parent, as we mentioned earlier. Okay, now we're going to figure out the total number of steps to turn a list into a max heap. Okay, so first we will look at how many leaves that we could we could have, right? So you think of remember we view, right? So we let me start a whiteboard. Okay, so remember this is how we view a list into a binary structure or binary tree. Okay, so and then you will have multiple layers, and then you get a high H. So this is a max heap. So we're going to call it H max, for instance. Indicates that this is for max heap, but it is the same even for min heap. So H max, if you build min heap, it's the same height. And then we're going to look at the leaf levels. The leaf level, how many leaf nodes we could have. Now remember, a leaf node, two of them will have a parent. So this is a leaf. So two of them will have a parent. So which means that the leaf nodes will be at most n divided by 2. Okay. So these will have a parent. For instance, you can see if let's say we use n to be 16. And let's use 10, right? As before. And what we have is A0, A1, A2, A3, A4, A5, A6, this is 3, 7, 8, 9, 10. So we have at the lower level, we have, so we got 4 leaves, and so we have height, right? So this is height is so the max height, so the lowest height. So this is the upper level. So this is upper level, even though these are leaves, but we only look at the lowest level. So then it's only 4. So 4 is less than n divided by 2. But so if you think of the full tree, then we will have, say, this is the maximum possible. So 11, 12, 13, 14. So we got 8 of those. Okay, so we get 8 nodes. And in this case, so n, so it's a 14, but the total number of nodes is 15 because we have this. So n 15 divided by 2, take the ceiling, and that is 8. Okay. And the height here is log n. Log n. So log 15. So here the height is a 3. So I'm sorry, 1, 2, 3. Okay. Uh, so we take, so the 15, so 15 is 2 to the, so it's less than, right? So we take the 4. So this is less than 2 to the, less than 2 to the 4. So take the 4, it's just 3. Okay, so that is what we have. And then to heapify, so we start from the last parent. So essentially that looks like this. So we have approximately n over 2 at the lower level. So at the lower level, they don't have any, uh, so these are already heapified. And at the upper level, you have n over 2 to the 2 many nodes. In that case, the level is 1. So this is at most, right? So this is at most. Is a big O. And then we keep on doing. So we got n 2. So the height is 2. And the number of nodes is 2 to the 3. And then you go to the max height. And there's only one node. So this is n over 2 to the max plus 1. So then what we need to figure out is this sum. Okay. So now let's move back to our slides. All right, so this is what we just get. Using a big O is upper bound, so we can just use a constant C to multiply that. All right, so then we simplify this form. So it's going to be a summation of h times n over 2 to the h plus 1, and h is from 1 to log n. And because this term it just becomes 0. And then we take the common factor out, so which is n. So going out, so what is left is h over 2 to the h plus 1. Just equal sign here. Okay, so and then this h is equal to 2 to the log h. So, and h is on top, so then this is going to be, and when you move it down, it becomes a negative. Okay, so that's why you have this term. Okay, and then this term, this one, to see why it sums up to a constant. It suffices to know that h over 2. So is greater than log h when h is sufficiently large. So this is obvious because log h is a lot smaller than h, and hence h over 2 is also greater than log h when h is not that. It doesn't have to be very big to make that to be the case. And then h minus log h will be greater than h over 2, and so this will be so this part So, so this is the same. So we don't need this. We just need this part. So 1 over 2 to the h plus 1 minus log h is less than this because h minus log h is greater than h over 2. So you put it down, so which is 1 over h minus log, or you can put a 2 here. That's still true. So then you put them down. So then 2 to the h minus log h would sweep the same side. So it's 1 over 2 to the h over 2. But then you have 1 here. So there will be have 1 here. And you have 1 here. Again, this is make it smaller at the bottom. So this is also going to be true. So then you sum them up. So this goes to a constant. Okay, so remember, right? So this part, h from 1 to log n, is just equal to 1 over 2. You can make it so you can think about so just write it down, right? So this h1, so this 1 over 2 plus 2 over 2 plus log n over 2, 1 over 2. So you put you put 1 over 2 down. So this will be 2 to the square root. And then this is 1 square root 2. Okay. Square root log n. So as you can see here, so you think about this 1 over square root of 2. Think about this will be your r. So this will be your r, so which is not equal to 1. Then it is equal to, when you sum them up, it's going to be equal to 1 over square root of 2 minus, so the log n plus 1 over 1 over square root of 2 minus 1. So when n is big, so this part becomes 0. Hence, what's remain is 1 is 1. So this square root of 2 going down, so that becomes 1 minus this is 1 minus that. So it becomes square root of 2 minus 1. So this is a constant. It's a positive constant. All right. So again, this type of a calculation, you should learn this kind of a skill from your calculus class. So put things together, then we know that to build a heap, for a linear list would only take n log n, big O of n log n time. And then we can now, once we have a heap, then we can sort the numbers also in n log n time. So to build a heap, okay, so this is how we build a heap. So build a heap takes linear time. To use this heap to sort numbers takes big O over n log n time. Okay, so so this is building a heap. And then once we build a heap, we can use this heap to sort numbers as well, not just doing priority queues. Okay, so in other words, for priority queues, once we build a heap takes linear time, then we can take the maximum out in constant time, and then we heapify the remaining part, so that only takes log n time once we have a heap, right? So in other words, so let's say I have a heap. So I'm going to remove the top because the priority queue, let's say remove it, and then the remaining part is already heap. So what we're going to do is I'm going to place this, the last node here, it is on top. And then I'm going to heapify this. So heapify this only goes into one branch. So that will only take log n time. So this idea can also be used to sort numbers. Okay, so to begin with, we have a max heap. So we take the max one out and then place this one on top, and then we heapify it. That takes log n time. And then heapify it, that means now in the remaining subtree, this is also the largest one, then I'm going to take it out. So when we take it out, we take the last one and place on top, and then heapify it again, and then we get the largest one here. Okay, so this way I get a sorted list in descending order. And for each numbers I extract, I will take log n time to heapify it. So we have n numbers. So altogether, to get a sorted list, it will take big O of n log n steps. So this is a implementation of a max heap. Pretty straightforward. Okay, so we defined heapify max. So what we do, and is for any I, right? So this is for any I, any internal node I. So its a left trial will be 2i plus 1. Its a right trial will be 2i plus 2. And then we compare I with L and R and place the largest one on top. So we first look at, see that if L is less than N, so which means that we do have children, so I does have left child. And then it compares with this left child. If the left child is larger, and then we place this index L. So index L to largest. And then we compare largest with this right child if it has it. So which means that if R is less than N, it also has a right child. And then you compare with it. And then if the right child is larger, and then you assign R to largest. Okay, and then once we figure out the largest, then we're going to swap them. So if the largest we figure out is not on the root, then we swap them by using a swapping statement. And then we will move, right? So we will move this internal node to the one we just swapped, then we keep heapifying it. So which is recursively call the function, but this time on the new index largest, which is the one that it gets the root down. So once we have this, when we heapify, so we will start from the last parent. So the last parent is n over 2, take the floor. So this is n double slash 2 minus 1. Okay, so so I will be in the range. Okay, starting from this. Now we move backward. So next time we'll subtract minus 1. Okay, and then until we get down to 0. Okay, so that's what this statement is. So for each of these, we are going to heapify it. So that is to build a heap, or called a recursive, sorry, it calls heapification from the last parent, and then move backward. So from right to left, and then from lower to higher level. And heap sort we already mentioned. So we first we build a heap. So we first build a heap, and then remove the root and replace the root with its last node in the list, and then we heapify it, right? So this is what it is. Remove the root, okay, swap, and then we heapify. So that's a heap sort. So that's descending order. You can also use a max heap to do this ascending order, but by changing their orders, right? So this is pretty straightforward. Okay, so that is how we do heap sort. And then once you have a max heap, to insert a new item, and then to make a heap is also pretty straightforward. And we could, for instance, if you have a heap already, so let's say I have a heap already. So this is a heap. And then I'm going to insert a new number. And what we can do here is that we're going to insert that number at the end. Okay, so what you need to do is that, so we're going to insert, so you may be, so this is your heap. So it could look like this, right? So this is the last level. Then you insert it here, and then you do heapification. Or it's already full, then you insert it here. Okay, and then you do heapification. So either way, to insert a node into a heap, and then to turn this new structure into a heap only takes log n time, because you'll just need to do heapification on one branch. And so this is a new node, and then you look at its a parent, and you move your way up when you do heapification, so that you only look at one branch. Okay, so that is the end of this video. Thank you for watching.